Very pleasant day to everyone. My name is Neha Priya. I'm working as an assistant professor in IMT College of Pharmacy. Today, my video lecture will be on the topic ultraviolet spectroscopy. So before moving further, let's see what are the contents of today's lecture. The contents of the today lecture will involve what is spectroscopy. As before jumping to ultraviolet spectroscopy, we need to have an idea about what does spectroscopy technique means. Then moving further, we'll discuss about what is ultraviolet spectroscopy, principle of ultraviolet spectroscopy along with Lambert-Beer's law, instrumentation of UV spectroscopy, and application involved in ultraviolet spectroscopy. So what does spectroscopy mean? Like what is spectroscopy? So basically spectroscopy involves two things. First one will be the matter. The matter can be atom or a molecule. And the second one will be the EMR, electromagnetic radiations. What happened here is, for an example, if I'm having a sample of certain compound, that compound will be having that matter will be having that sample will be having a molecule and atoms in it. When I give a radiation to the sample, what happened will be there may be an absorbance of the radiations, there may be a transmission of the radiation, like the some of the radiation will transit, and the third one will be a scattering of a radiations. So all these phenomena come into the spectroscopy, and the instruments which work on these techniques is known as spectrophotometers. So basically the first one, what spectroscopy mean, is clear now. Now the second one, what we need to learn is ultraviolet spectroscopy. So basically the region of 200 to 400 is known as UV wavelength region, and the visible wavelength region will be the 400 to 800 nanometer range. What happened in ultraviolet spectroscopy is there is a transmission of molecules from low energy state, electrons from low energy state to high energy state. For an example, if I'm giving a molecule get the radiation, it will transit its electrons in low energy state to high energy state. In a molecule, certain things can happen when we give them a radiations. That things can be, first one is electronic transition, second one is rotational change, and third one is vibrational change. So rotation and vibration go for IR spectroscopy, and ultraviolet spectroscopy involves electronic transition of a molecule. Basically, the use of ultraviolet spectroscopy is it measures the number of conjugated double bonds and also aromatic conjugations within the various molecules. It is also used to distinguish between conjugated, non-conjugated, unsaturated carbonyl compounds, and further to determine the absorbance and impurity present in any of the compounds. So what does the principle of ultraviolet spectroscopy? For an example, I'm having a sample, I'm giving it a radiation. What will happen? The the molecule will go from low energy state to high energy state, stable state to unstable state. And these electronic transition of the molecules from low energy state to high energy state is the principle of UV spectroscopy. This will get us the result. This will analyze the particular like quantity, quality, and measure the and analyze the sample. So when I'm doing a sample ultraviolet spectroscopy, what I'll get is the maximum absorbance of that sample, and these maximum absorbance can be termed as lambda max. The lambda max is very unique, as the lambda max is same for all of the sample. It will always be the same. If the concentration also increases, the lambda max of the sample will remain the same. Yet if I'm using like increasing the concentration or decreasing the concentration, the absorbance of that particular sample will decrease. For an example, if I'm having a sample with me, I'm preparing PCM of 0.1, 0.2, 0.3, 0.4, 0.5. The wavelength, the lambda max of PCM will remain the same. If it is 293, lambda max is 293, then it will be 293 for all of the concentration. Yet the absorbance of all of the concentration will increase or decrease in whatever order it will be. If it is in the 0.1, we can take it will increase, and if I take it from 0.5 to 0.1, it will decrease. But absorbance depend upon the concentration, but wavelength doesn't. Lambda max didn't depend on the concentration of a sample. As I've already told you, the electronic transitions. So what is happening here is from electrons, the molecule, when molecule get the radiation, its electron will move from low energy state to high energy state, like unstable state to unstable state. And these electronic transition is the reason why we are getting the result, why we are getting this change determine the sample. This change in a molecule will determine the, it will do the analysis of a sample. For an example, like if I'm having a molecule of PCM, then this molecule will change its direction from low energy state to higher energy state, and these transition will determine how much transition is happening over here, and these transition will tell me the lambda max of a sample. As I know, there are certain transition that will happening over here. This transition will be sigma to sigma star, n to sigma star, pi to pi star, n to pi star transactions. Let's take an example for the same. This diagram will give you the electronic transactions graph. Here you can see the transaction will be sigma to sigma star. Sigma is the low energy state. Higher energy will be the sigma star. Then pi to pi star, n to pi sigma star, and n to pi star. Depending on the substance, these transactions can occur. Let's go with sigma to sigma star. In sigma to sigma star, the wavelength is very small, and to determine this small wavelength, we need to require a large quantity of large amount of energy. So the energy used in sigma to sigma star will be more, and the wavelength will be less. For an example, methane, ethane, propane, and cyclopropane. Then moving further, we have N2 sigma star. In this, particularly what we determine will be the saturated compounds with an unshared pair of electrons. Here, what will be happening will be the wavelength will be more than sigma to sigma star, and the energy wavelength will be more than sigma to sigma star, and the energy required will be the less than sigma to sigma star. Example for the same will be saturated halides, as alcohol, ethers, amines, etc. Moving further to the pi to pi star transition, what happened here is we determine the unsaturated center of a molecule. Basically, it occurs in unsaturated center of a molecules, and the energy required for this will be more than less than sigma to sigma star and n to sigma star, but the wavelength will be more than that. The wavelength will be more than the upper two transitions. Example of the same will be alkenes, alkynes, carbonyl compounds, azo compounds, etc. The last one will the n to pi star transition. It will be happening in unsaturated center of a compound with have unshared electron pair of heteroatoms. This transition will have the minimum amount of energy will be required for this compound, and the wavelength will be more for this amount type of compounds. So the electronic transition that will be occurring in a UV spectroscopy will be sigma to sigma star, n to sigma star, pi to pi star, and n to pi star. The second topic will be the chromophoric agent that is responsible. These agents are very much important as these agents give the color to a compound. These important, like absorption can only occur if a compound is having certain color, and these compounds give color to a compound. These are responsible for that. Basically, we can say it as a color giving compounds. Color giving part of a the substance which give color to a compound can be termed as chromophore. The example for the same will be ethylenic, acetylenic, carbonyl acid, esters, nitrile group, etc. The further we have oxochrome. Oxochrome intensify the chromophore intensity. For example, if a chromophore is not having chromophore is having certain intensity, it will increase in intensity so the detection will be useful. The example for the same will be OH, OR, NH2, NHR. If these compounds are available in a chromophore, if these groups are available in chromophore, they'll increase the intensity of a compound. They will increase the detection, they will increase the color of a compound. So chromophore and oxochrome are related to each other. Basically, chromophore is color giving, gives color to a compound, and oxochrome is chromophore is responsible for presence of color in a compound, and oxochrome is enhancing the intensity of a chromophoric part of a compound. If I'm getting a result, then there will be a graph, and these graph can be turned as spectra. Then this spectrograph can have certain shifts depending on the result I'm getting. We can classify it into 4 parts. The shifts can be classified into 4 parts. These parts will be bathogramic, hypsochramic, hyperchromic, and hypochromic. The first one will be bathochromic shift. When the absorption maxima shift towards the longer wavelength, like the absorbance maxima increases, the lambda max changes, it increases, that can be termed as bathochromic shift. When the absorption maxima shifted towards the shorter wavelength, that can be termed as blue shift, or we can say it as hypsochromic shift. Then hyperchromic and hypochromic. In hyperchromic, when the intensity of absorption maxima increases, the absorbance increases, then we can call it as hyper. And hypo goes for when the intensity of absorption maxima decreases. It can like decrease to a small unit, or to a like it will drastic change in the compound can also happen, and the small change can also be termed in a smaller side can be termed as hypochromic shift. Then there are two laws that are involved in ultraviolet spectroscopy. We'll go for both of two laws, but before that, I'll give you an example. Like if I am having a different concentration of PCM. For example, I'm having a concentration of 0.1%, 0.2%, 0.3%, 0.4%, and 0.5%. And I'll analyze it into a UV spectroscopy. So what will happen there will be there. What happened there is, like a compound is giving a radiation, the amount of radiation absorbed with 0.1% of PCM will be smaller than the amount of radiation absorbed by 0.2%. So I can say that absorbance is directly proportional to the concentration of a compound, because as the concentration increases, the absorption of the compound will increase. It may be a drastic increase or a smaller increase, but the concentration of a compound will increase. So the A is equals to absorbance is directly proportional to concentration. Then further, if I'm having a compound, for an example, and I'm having a compound, the concentration are same, but the path length differs. For example, I'm having one for compound, I'm having this much of path length for the radiation to go, then the radiation will have this much time only with the sample, and the amount of radiation absorbed will be less. There, and I am having this much of path length, the amount of time the radiation will be with the sample will be more, so thus the absorbance within that period of time will be more. Can I say, then I'll say that absorbance is directly proportional to path length too. Let's state that Beer stated that absorbance is directly proportional to concentration, and Lambert stated that absorbance is directly proportional to path length. Combining these two laws, I can say absorbance is is equals to epsilon Cl or ABC. That is, A for capital A goes for absorbance, small a goes for a constant, B is for thickness, and C is your concentration. Then when I will be doing this, there can be a certain deviation that can occur within the sample. For an example, there can be a positive deviation and a negative deviation. Whenever there is a small change in concentration and there is a great change in the absorbance, that can be that situation can goes into a positive deviation situation. But when there is a small, like large change in the concentration, if I will be using 0.1 and the last I will be using a 10%, but there is a small change in the absorbance, then there will be a negative deviation. Linear goes for the constant change in absorbance, goes for a linear change. So there are two types of deviation that can occur in a sample. That first one is positive deviation and the second one is negative deviation. Let's now further move to the instrumentation of UV spectroscopy. If I go for instrumentation of UV spectroscopy, let's learn it with an diagram. What happened here is, first one, whatever, like if I'm doing a UV spectroscopy or any spectroscopy, the first thing I need is a matter, a sample and a radiation. And the first thing here is also a source of radiation. When a source of radiation give you the radiation, it will go to filter and monochromator. What filter and monochromator will do is, filter and monochromator will like emulsify. Basically what they'll do is convert polychromatic into a monochromatic light and split it to the both of the cells, reference cells and sample cells. Then reference cells, we'll go for the reference, the solvent we are using in the sample, we'll put our sample with plus solvent. Then further, photodetector will detect the results from both of the sample cells, and then further amplifier will amplify and detect and readout will show you the results for the same. Let's start with source of radiation. What we need in the source of radiation, the first thing we require in the source of radiation will be, it should be stable. Like if I'm using a source of radiation, what I want is, if I want 249 wavelength, then source of radiation should give me constant 249 radiation. It should not vary, it should not fluctuate. It should not be like that if I'm using an instrument for 2 hours, then it is going to fluctuate. No, it should be, continuing use. If I'm continuously using the instrument, it should be constant for a longer period of duration. So these are certain requirements that we will be needing from the radiation source. Now the first thing I'll be having is, like, I'll just discuss it with you in a short in a like general manner. Basically, in radiation source, what we need is, like, if I'm having a glass, like a compact glass or a cylindrical glass. And in that cylindrical glass unit, I'll just put a gas, inert gas at a high atmospheric pressure. Then what happens is, when I provide them the energy, and I'm providing it an energy when I'm providing it an energy, the vibration, like there will be the glass will heat up, the system will heat up, and it will produce certain energy. For an example, it can give you radiations, sorry, for example, it can be a vibration, it can be electron discharge, and because of that the radiation is produced. So what happens in tungsten halogen lamp is, there is the like the thing that is present out here will be, the inert gas that is present here will be He and Ar. When I give it a energy, it will just increase the temperature, and when the temperature is increased for the same, it will generate radiation. The second one will be the hydrogen discharge lamp. As I already told you, take it as a component only, as a cylindrical shell. In this, H2 gas is filled. When this H2 gas is filled, I'll produce a current. When the high current is given to the same, there is a discharge of electron, and these electrons will be responsible uh, for exciting the hydrogen molecule. And when hydrogen molecule will get excited, it will emit UV radiations. Let's go to the third part, that is the mercury arc lamp. Mercury arc lamp and xenon lamp are the most useful lamp radiation source we use. But the demerit of mercury arc lamp is that, like, it can't be used for a longer duration. We can't use it for 24 hours as it will heat up. But it has a accuracy, that's why it is mostly used. Mercury arc lamp, as you can already see in a diagram, in between cathode and anode, there is the presence of mercury vapor stored, and the same thing will happen when we giving him that electric current. The discharge of electrons, because of the discharge of electrons, the molecule will get excited, and when the molecule will get excited, there will be the production of radiation source. The fourth one, and the last one, is xenon discharge lamp. As you can see here, the instrument will be filled with a xenon gas, and by applying a high voltage, will get the radiation. It is a very good instrument. It has been used in most of the instrument in analysis. The second part is that instrumentation. The second part involved in the instrumentation will be monochromator. What monochromator will? That will convert a polychromatic light into a monochromatic light. It will also split the lights into two parts, that will be to the sample and to the reference cell. Sample and reference cells, this may differ. As for one beam spectroscopy, one beam ultraviolet spectroscopy, there is the presence of only one slot. What happened there is, the first thing I'll do is, I'll prepare my sample. After preparing my sample, the first time I'll put in single beam spectroscopy, I'll put the solvent or the blank in the cuvette and place it into the instrument. I'll run the instrument, do the baseline correction. Then after the baseline correction, I'll take out the cuvette, fill it with the sample, put it in the same place, and go for the wavelength determination. But in, say, double beam spectroscopy, what I'll do is, I'll take both of the cuvettes, I'll fill it with the solvent or the blank, put it in the instrument, run the instrument, do the baseline correction. Then I'll remove just the samples cuvette from the sample cell. Reference cell will have the same sample or the blank will be constant out there. I'll take the qubit from the sample cell, fill my sample over there, put it into the instrument and do the process. I'll get my lambda max. Why we are going for the blank? Why we are correcting the baseline? It's because the sample absorbance should not get affected by the solvent. I should not get disturbed by the solvent. If there are certain impurities with the solvent, that should be corrected. The baseline of the solvent should be minimized so that I'll only get the lambda max of my sample. I will only get the absorbance of my sample. It should not get interfered by the blank or my solvent, whatever solvent I will be using. The last one will be the detector. Detector mainly, the detector is the main part. The only thing I need you to have in mind is potential difference. All the detectors work on the same principle, that is the potential difference between cathode and anode. So the first one and the most useful one, that this detector is used in like all of the ultraviolet spectroscopy techniques. The first one is photomultiplier tube. What happened here is, there's the, like you can see in the diagram, the first part is cathode side and the second side is anode side. The radiation comes, it interact with the diodes and get multiplied. First time, the first one radiation come, diodes like it will get involved with diodes, it will convert into 2, then for the 4, then for the 8, then 16 and so on. It will get multiplied, and when it get multiplied, there will be a potential difference from on the both of the side, from the cathode side and anode side, and because of this potential difference, we'll get the analytical report for the same. The second will be photovoltaic cell, or we can say barrier layer cell. Barrier layer cell itself says that there will be some layers. So these layers will be silver, selenium, and iron layer. What happen here is, when the radiation will get to the silver, when like the quantity of radiation comes to the iron will be very small. So there will be difference, potential difference from upper side to the lower side, and because of this potential difference, we get the result. The last one is a photo tube. What happens out here is, like, this is my cathode, this is my anode. When a radiation is coming, the radiation, the amount of radiation this anode will get is very small to the amount of radiation this cathode will get, thus making a potential difference between cathode and anode side, and because of this potential difference, I'll get the result. After getting the result, all this result will be amplified, and then after amplifying, we'll get it on our recording devices. After getting the device, we can analyze our sample. So let's move to the last topic, that will be applications of ultra UV spectroscopy. So basically, the applications of UV spectroscopy includes, first one will be the detection of impurities. It will determine the impurities. As I can take an example. For example, I am having PCM. The and the lambda max of PCM should be 297. Let's take 297. And I'm having a different sample from a different company. I'll check with the lambda max of PCM of original one and this one. If the lambda max differ, then there is the chances that sample from the different company have certain impurities. By this analysis, I can get the result that this sample or this sample is having impurities in it. The second one will be structural elucidation of organic compounds, followed by quantitative and qualitative analysis for spectrophotometric titration and determination of purities in single component and in multi-component analysis. Thank you for your time. Thank you.